Hello everyone, today's video is on spring in combination. After watching this video, you'll be able to calculate equivalent spring stiffness, complete your weekly tutorial problem, and apply this concept into vibration system to find natural frequency of the systems. Often in application, springs are placed in combination. It is convenient for the purposes of modeling and analysis to replace the combination of spring by a single spring of an equivalent stiffness. So, for a model like this of single degree of freedom consisting of a block attached to a spring of an equivalent stiffness K equivalent, which is subject to a force F and has a displacement x, can be written as F equal K equivalent x. Let's consider two springs in a system are connected in series. In this case, the force developed in each spring is same. However, the displacement of the block is the sum of displacement of the springs connected in series. So we can write x equivalent equal x1 plus x2. From equation 1, we can write F by K equivalent equal F by K1 plus F by K2. So, therefore, the equivalent spring stiffness for the series connection can be written as 1 by K equivalent. Therefore, the equivalent spring stiffness for series can be written as 1 by K equivalent equal 1 by K1 plus 1 by K2. Now let's consider another two springs in a system are connected in parallel. In this case, the displacement of the spring are same. However, the force developed in the block is the sum of the force developed in each spring. So we can write F equivalent equal F1 plus F2. Again, from equation 1, we can write xk equivalent equal xk1 plus xk2. Therefore, equivalent spring stiffness for parallel spring can be written as K equivalent equal K1 plus K2. Let's find an equivalent stiffness of the system using these two equations. So, first step would be draw the ground. In second step, count how many springs are attached to the ground. So we found K1, K2 and K4. So we write K1, K2 and K4. Next step would be draw all the springs that are connected to the ground. So we connect the spring K1. Sorry, it should be K1, K2 and K4 connected to the ground. In step 4, see what is attached to the other end of the spring. So for K1, it is attached to the K3, so free and K1 is connected to K3, free end of K2 is also connected to K3, free end of K4 is connected to mass. Here you. Alright, in step 5, attach the remaining spring where in contact and leave the mass out of the spring for the time being. So, this is the ground, K1 and K2, they're connected to K3, and this is K4. Let's leave it that way since it is connected to mass. In step 6, repeat step 4 and 5 until all the remaining free ends to be attached to the mass. So, again, free end of K3 is attached to the mass. You can see from here, free end of K4 is attached to the mass. We can see from here. in step 7, attach the mass. So we draw the diagram where K1 and K2 were connected to K3, and this is K4, and K4 and K3 are connected to mass. Alright, so we get the free body diagram of the cyst given system. Now we need to find equivalent spring stiffness in step 4. Since K1 and K2 are connected in parallel, so we can write their equivalent spring stiffness as K12, and it will be K1 plus K2. Alright. Then this K12 is connected to K3 as a series, so we can write 1 by K1, 2, 3, which is the equivalent of this system, and we can write 1 by K12 plus 1 by K3. Now K1, 2, 3 is connected to K4 as a parallel, so we can write their equivalent spring stiffness as K1, 2, 3, 4, or K equivalent for this system, and we can write as K1, 2, 3 plus K4, and that is your answer to find the equivalent spring stiffness for the system. So from this video, you were introduced to equations for equivalent stiffness for springs connected in series and parallel, and learn how to calculate equivalent spring stiffness for the given system. These concepts will help you to complete your weekly tutorial problem and to find natural frequency of the given system.